Hello students, in my previous lecture I explained the two modes of conduction for rectifier controlled DC motor drive, that is continuous conduction mode and discontinuous conduction mode. We discussed the waveforms in both the cases in detail, and we had seen that how the power flows in different parts of the cycle in both the conduction modes. Now, in today's lecture, we shall do the steady state analysis of rectifier controlled DC drive when the conduction mode is continuous. So, later on in the next lecture, we shall discuss what happens when the conduction is discontinuous. So, if you see the waveform drawn here, it is the waveform of armature voltage for continuous conduction mode, where alpha is the firing angle. So, when the thyristor T1 and T3 are triggered, output voltage becomes equal to Vm sin omega t, that is equal to Vs. So, and after that we trigger the next pair of thyristors and the output voltage becomes equal to minus Vs. So, the waveform is like this. It starts from alpha, and after pi plus alpha the waveform repeats itself. Or you can say that the frequency of variation of output voltage is half, or you can say that double the frequency of variation of input voltage, that is source voltage. So, if you want to find the average value of this voltage, you have to integrate this voltage from alpha to pi plus alpha or from 0 to pi. So, for convenience, I will take the cycle from alpha to pi plus alpha. So, let us try to find out what is the average output voltage. So, what is average output voltage? And that voltage you have to integrate over the whole cycle of variation, and this is from alpha to pi plus alpha, and during this interval the output voltage remains equal to Vm sin omega t, that is equal to Vs. So, this is Vm sin omega t, and then you have to divide it by the period of the cycle, and that is equal to pi. Alpha to pi plus alpha, that is duration is nothing but pi radius. So, just integrate it and put the limits, and what you will get here, it will be 2 Vm by pi cos alpha. So, this is the average value of output voltage in the case of continuous conduction. And you can say that alpha can be varied, theoretically you can vary alpha from 0 to 180 degrees. So, cos alpha will be 0 when alpha equal to 90 degrees. Before that it will be positive. For alpha equal to 0 it will be equal to 1, and for alpha equal to pi radians it will be equal to minus 1. So, you can say that Va is equal to 2 Vm by pi for alpha equal to 0, that you may call as Va max. The maximum value of average output voltage will be for alpha equal to 0, and for alpha equal to 90 degrees or pi by 2 radians, Va will be equal to 0, and for alpha equal to, say, the maximum value of alpha equal to pi, what is Va? Va will be equal to minus 2 Vm by pi. So, that is, you can say that it is nothing but it is equal to Va minimum value, that is equal to minus of Va max. So, output voltage will be Va max, that is equal to 2 Vm by pi. So, this is Va max, and it will be Va min, that is minus Va max. So, output voltage varies from Va max, that is 2 Vm by pi, to minus 2 Vm by pi, and alpha is varied from 0 to pi radians. So, this means that there are two situations. Once Va is greater than 0, that is positive, and when the Va is less than 0, that is it is negative. So accordingly the machine can behave in two different quadrants. You can see that current here cannot be negative because here thyrstors are there, they are connected like this. So this figure shows the, you can say, the diagram of rectifier controlled DC drive. Here this symbol shows it is a controlled rectifier. Thyrstors is shown, so it is a controlled rectifier. This is the input supply, is sinusoidal. It can be 3-phase or it can be single phase. Presently we are discussing single phase supply rectifier. So it is single phase supply. It can be 3-phase also. Same symbol can be used there also. So there is single phase supply is given here. There are thyrstors and current cannot flow in the reverse direction. This means that current has to be always positive. But as we have seen here, output voltage can be both positive and negative depending on value of alpha. So you can say that there are basically two modes of operation or two quadrants in which the machine can operate. So let us first discuss the first quadrant operation. First quadrant means quadrant of speed versus torque plane. So this will be possible when VA is greater than 0 or alpha is less than 90 degrees. First quadrant means it is forward motoring operation. So for motoring mode, what is the requirement? That current should flow like this and the torque produced should be in the direction of speed. So suppose the machine is rotating in the forward direction, I am calling this direction as forward direction, and current flowing like this, torque is produced in the same direction. Or you can say that current is, and here we have made one assumption here that devices are ideal, that is voltage drop in the thyrstors and diodes connected here are 0 and the flux of the motor is kept constant, that is field winding is given a constant voltage supply. So these are the assumptions that we had made. So here you can say that if you make alpha greater than 90, less than 90 degrees, output voltage is positive and current flows like this provided VA is more than E. So you have to maintain alpha such that the output voltage is greater than E. In that case the current flows like this and the energy flows from this rectifier side to the motor side. So average energy in one cycle will be positive, that is it flows like this. During this one part of the cycle, here in this case you can see that here the current that we had drawn earlier, it was somewhat varying like this. So during this interval the power flow will be negative, but overall power, average power always flows from rectifier side to motor side, and you can say that it is the motoring operation. The machine is behaving as a motor. So it is first quadrant operation. Torque is positive and speed is also positive. So power flows from source to motor, that is average power. During this interval some part power may be negative, but the average power will be positive. So it is called the first quadrant operation. Now as you can see that current cannot reverse. So if you recall what I mean by the different quadrants, so this is the speed on this side and here I have sent the torque. So when the speed is positive, torque is positive, we call it for first quadrant operation, that is the forward motoring operation, and when torque is positive but the speed is negative, we call it fourth quadrant, that is reverse braking operation. Speed is positive but the torque is negative, we call it third quadrant operation, that is the forward braking operation, and when both speed and torque are negative, we call it fourth quadrant operation, that is the reverse motoring operation. So for reverse motoring and reverse braking, the torque has to be negative, and as you have said that flux is constant, flux is not reversed. This means that for torque to become negative, current has to be negative. But here you can say that current can never flow in the reverse direction, so current cannot be negative. So this means that third quadrant and fourth quadrant operations are not possible in the rectifier controlled DC drive without any change in the connections. With there are some techniques in by which you can operate the machine in the third and fourth quadrant, but as such, as for this connection, this is not possible. But the fourth quadrant operation is possible. So let us see what is the fourth quadrant of operation. And as you can see that this is possible only when VA is less than 0 or alpha is greater than 90 degrees. So when you reverse the output voltage by making alpha greater than 90 degrees, here you have made alpha greater than 90 degrees. So as per this equation, output voltage will be negative. So the polarity of average output voltage will be now reversed. And if the current flows in the same direction, and you can say that armature current flows like this, so power flows back from motor to source. So in that case, the this machine behaves as a generator. That is, it generates energy and it feeds back the energy to the source. But how it is possible? If this is the situation and you have just reverse alpha, then current can never flow in the positive direction. For current to become positive with alpha more than 90 degrees, only possibility is that the polarity of back EMF or armature EMF should reverse. Only then current can flow in the, because this is positive, this is trying to flow the current in the reverse direction, but current to flow in the positive direction, for that the polarity of the back EMF has to reverse. It has to become negative, and it has to be like shown in this figure. So the polarity of E has to be opposite to what it was in the case of forward motoring mode, and that too the value of E should be more than VA for current to flow in the clockwise direction. So this means that for this mode of operation, alpha should be greater than 90 degrees, making VA less than 0. But you have to maintain that E should also reverse. E should also reverse, and the magnitude of E should be greater than magnitude of VA. Then only current can flow in the, average current can flow in the positive direction. So this means that, and how E reverses? If you recall the equation of back EMF, it depends on phi and speed. Phi you have kept constant. So this means that for reversal of back EMF, the speed has to reverse. So this means that the speed has to reverse, so it will become the counterclockwise direction. If it was clockwise in the earlier case, it has to become counterclockwise direction, and we have to maintain VA such that magnitude of VA is less than magnitude of E. So we have to maintain such a value of alpha that causes magnitude of VA to be slightly less than E, so that current flows in the clockwise direction. In that case, the machine starts behaving as a generator, and this is possible only when speed reverses by itself, and this will happen in the case of when the motor is connected with some active load torque. It is not possible for the passive load torques. For active load torques, such as some train is moving across the slope, and after certain value the speed reverses, train goes in the reverse direction. Or you can have some lift which is operating such that the speed has reversed because of the torque of the that pulley and torque of the counterweight, and that will cause reversal of speed and reversal of the bike cable. So for this coordinate, it is necessary that the machine is supplying some active load torque, and that load torque is now driving the machine. So the mechanical energy comes from that active load torque, active load, and that is driving the machine in the reverse direction. That has caused E to reverse, and to maintain a positive torque, you have to alter alpha, you have to gradually increase alpha and make it beyond 90 degrees and maintain such a value of alpha that causes VA to be slightly less than E, so that current continues to flow in the reverse direction, and that will cause braking operation. And you can say that torque is still positive, still speed has reversed, so the torque generated by the machine will oppose the motion, and it will be a braking operation or the generating operation, and energy will be fed back to the source. So these are the two possible modes of operation in the case of rectifier controlled DC drive. And as I said earlier, the third and fourth quadrant operation is not possible in such type of drives. So that is all for this lecture. Thank you very much.